a sunspot cluster 90% the size of the one that nearly destroyed civilization in 1859 just rotated into view, and it is aimed directly at Earth. Right now, as you listen to this, magnetic field lines are twisting beneath the surface of that dark patch, building energy that could release in seconds. NASA's Perseverance rover spotted it from Mars before we even knew it existed. NOAA split it into 3 separate numbered regions because a single designation couldn't capture its complexity. It has already fired an X-class flare while we weren't looking, on the far side of the Sun. And here is what nobody is saying out loud. We have entered December 2025 with multiple coronal mass ejections already in flight, racing toward our planet at speeds that break every model we have. The convergence is happening. Stay with me until the end, because what I am about to show you will change how you think about the next 6 months. Before we begin, like and subscribe if this calm, science-driven format resonates with you. Use the hype button if it is available. In the comments, note your location, your current time, and the key question this topic triggers for you. I will address the strongest questions in comments or in a later video. The monster awakens. AR4294 emerges from the far side. The first image came from Mars. On November 21st, 2025, NASA's Perseverance rover was conducting routine solar monitoring from Jezero crater when its instruments detected something unusual on the Sun's far side. A massive surge of X-ray emissions originating from a region of the solar surface that Earth-based observatories could not yet see. The signature was unmistakable. An X-class flare, one of the most powerful categories of solar eruption, had just exploded from a sunspot cluster that was still hidden beyond the Sun's eastern limb. The rover's data was transmitted back to Earth, arriving at the Deep Space Network stations with a strange kind of urgency that automatic systems rarely convey. Someone at the Jet Propulsion Laboratory looked at those numbers and understood immediately what they meant. Whatever was coming around the bend was not small. It was not quiet. And in approximately 7 days it would be facing our planet directly. The waiting began. Solar physicists have learned to read the Sun's surface the way doctors read an EKG, watching for the telltale signs of instability that precede catastrophic release. When a sunspot cluster produces an X-class flare while still on the far side, it sends a clear message. This region is magnetically complex, energetically primed, and capable of directing significant violence toward whatever happens to be in its line of sight when it rotates into view. By November 28th, the leading edge of the cluster had rotated far enough that Earth-based telescopes could catch their first glimpses. What they saw sent a ripple of quiet alarm through the space, weather community. The cluster was enormous. Active Region 4294, as NOAA's Space Weather Prediction Center designated it, measured nearly 200,000 kilometers across at its widest point. For context, that is roughly 16 times the diameter of Earth. But size alone does not determine a sunspot's threat level. The truly dangerous factor is magnetic complexity, and AR4294 possessed that in abundance. Solar magnetograms revealed a beta-gamma-delta configuration, which is the technical designation for a sunspot region, where magnetic field lines of opposite polarity are twisted together in extremely close proximity. Imagine 2 powerful magnets forced face to face with their opposing poles touching, held in place by forces they constantly strain against. That is the state of the magnetic fields threading through AR4294. The tension is immense. The potential for sudden, violent reconfiguration is high. But here is where the story takes an unexpected turn, one that reveals just how much we still do not understand about our own star. As AR4294 continued to rotate into Earth-facing position, additional observations revealed that it was not alone. 2 more massive sunspot clusters were following behind it, separated by only small stretches of relatively quiet solar surface. NOAA made the unusual decision to assign separate designations to all 3, AR4294, AR4296, and eventually AR4298. Each maintained its own magnetic complexity. Each demonstrated independent flaring activity. But they were close enough and magnetically interactive enough that some researchers began referring to them collectively as a single superstructure. The implications of this arrangement are not immediately obvious, but they become clear when you consider the mechanics of coronal mass ejections. When a sunspot releases a CME, it launches a bubble of magnetized plasma into space. That bubble travels outward from the Sun at speeds ranging from a few hundred to several thousand kilometers per second, depending on the energy of the eruption that produced it. If multiple sunspots in close proximity fire CMEs within a short time window, those plasma bubbles can interact during their journey. They can merge, amplify, create shock waves that accelerate particles to near relativistic speeds. The resulting composite structure can be far more dangerous than the sum of its parts. This is not theoretical concern. This is documented phenomenon. The July 2012 solar storm, which narrowly missed Earth and would have caused a Carrington-level event had it arrived 9 days earlier, was produced by exactly this kind of multi-region interaction. So the appearance of AR4294, 4296 and 4298 in close formation was not just noteworthy, it was ominous. By December 1st, all three regions had rotated fully into Earth view. Solar observatories around the world turned their instruments toward the cluster complex, and the data began flowing in. High-resolution magnetograms from the Solar Dynamics Observatory, H-alpha imagery from ground-based telescopes showing the intricate structure of solar prominences arcing above the active regions, radio emissions at multiple wavelengths revealing plasma temperatures and densities in the lower corona. And then, as if aware of the scrutiny, AR4294 fired. An X1.9 flare erupted from the leading sunspot at 0249 UTC on December 1st. The flash was captured by multiple satellites, each recording different aspects of the event. Extreme ultraviolet cameras showed the initial brightening, a sudden spike of emission at wavelengths corresponding to plasma, heated to tens of millions of degrees. X-ray detectors registered the surge of high-energy radiation streaming outward from the flare site. Radio telescopes picked up the Type II emission, the telltale signature of a shock wave propagating through the solar corona. That shock wave was the evidence that a coronal mass ejection had been launched. Coronagraph imagery from the Solar and Heliospheric Observatory confirmed it within hours. A halo CME, visible as a bright ring expanding outward from the occulting disk that blocks the sun's glare, indicating that the plasma cloud was moving more or less directly toward or away from the observer. Given the location of AR4294 near the sun's northeastern limb at the time of the eruption, trajectory analysis suggested the CME would deliver a glancing blow to Earth's magnetosphere sometime around December 3rd or 4th. But the X1.9 flare was not the end of the story. It was barely the beginning. Over the next 72 hours, AR4294 produced a barrage of M-class flares, each one representing a significant release of energy, each one with the potential to launch additional CMEs. The region was essentially in a state of continuous eruption, with magnetic field lines breaking and reconnecting every few hours, sometimes every few minutes. On December the 6th, AR4299, a newer region that had emerged near the Sun's north-central area, produced an M8.1 flare. The associated CME was a full halo event, meaning its trajectory was directly Earth-aligned. NOAA's Space Weather Prediction Center issued a G3 geomagnetic storm watch, upgraded from the previous G2 watch, as models refined the CME's expected arrival time and magnetic field orientation. The watch predicted storm conditions beginning early morning December 9th UTC, with possible escalation to G4 levels if the CME's magnetic field aligned in an unfavourable configuration when it struck Earth's magnetosphere. This is the point where most news coverage would have stopped. Storm watch issued, auroras predicted at lower than usual latitudes, mild warnings about GPS, disruption, and potential power grid stress. The standard narrative of space weather events that we have all become familiar with over the past few years as solar cycle 25 has ramped up to its maximum phase. But there is a deeper layer to this story, one that requires us to zoom out from the immediate events and look at what AR4294 actually represents. Because when scientists began comparing the physical dimensions and magnetic characteristics of this sunspot cluster to historical records, they discovered something that nobody had quite expected to see during this solar cycle. AR4294, when measured by total area and magnetic flux, is approximately 90% the size of the sunspot cluster, that British astronomer Richard Carrington observed on September 1st, 1859, the same cluster that, later that day, produced a white light flare so intense that Carrington saw it with his own eyes through his telescope's solar projection system. The same cluster that launched the most powerful geomagnetic storm in recorded history, one that caused auroras visible in the Caribbean, set telegraph stations on fire, and induced electrical currents strong enough to allow some telegraph operators to send messages without batteries. 90%. Not similar in general character, not vaguely comparable. 90% of the measured area, based on careful comparison of historical sketches and modern high-resolution imagery. This raises an immediate and uncomfortable question. If AR4294 is 90% the size of the Carrington Event sunspot, is it capable of producing a 90% strength Carrington Event? The answer is complicated, and the complication reveals something profound about how much uncertainty still exists in our understanding of solar physics. Sunspot size correlates with flare potential, but it does not determine it. The Carrington Event flare was estimated to be an X45, based on its effects and on reconstruction of the event using modern space weather models applied to historical magnetogram data. That is 5 times stronger than the most powerful flare recorded in the past decade, an X9.0 that erupted from AR3842 on October 3, 2024. But here is the thing. The X9 flare from October did not produce a Carrington-level geomagnetic storm. It produced significant aurora displays and some minor technological disruption, but nothing approaching the scale of 1859. Why? Because the flare's location near the Sun's western limb meant that the associated CME was not well aimed at Earth. The plasma cloud mostly missed us. Location matters, timing matters, the orientation of the erupting magnetic structure matters, the pre-existing condition of the solar wind matters, because a fast CME travelling through already disturbed space can create a much more severe impact than the same CME travelling through quiet conditions. All of these factors are difficult to predict with precision, even with our modern fleet of solar monitoring satellites and sophisticated computer models. We can see a dangerous sunspot rotating into Earth view. We can measure its magnetic complexity. We can watch it produce powerful flares and launch CMEs toward our planet. But we cannot say with certainty whether the resulting geomagnetic storm will be a minor G1 event that produces pretty auroras at high latitudes, or a major G5 event that threatens power grids and satellite infrastructure across entire continents. What we can say is this. AR4294 and its companion regions represent the most magnetically complex and energetically active sunspot cluster to face Earth since AR12515 in March 2015, which produced multiple X-class flares and several significant geomagnetic storms. Before that, you have to go back to October 2003, when AR486 unleashed the Halloween storms, including an X28 flare that remains one of the most powerful ever recorded. So we are looking at a once-per-decade scale event, possibly once per 2 decades, rotating into optimal position for Earth impact at a time when we are already at solar maximum, when background solar wind conditions are elevated, when our magnetosphere is already stressed from previous storms. The convergence I mentioned at the beginning is not metaphorical, it is literal. Multiple CMEs are currently in transit between the Sun and Earth. They will arrive in sequence over the next several days, each one capable of driving geomagnetic activity to storm levels, each one potentially interacting with the ones before and after it to create compound effects that exceed simple addition. And AR4294 is still facing us, still magnetically complex, still capable of producing another major flare at any moment. Solar maximum's broken promises and shattered predictions. We need to talk about how wrong the experts were. In December 2019, an international panel of solar physicists convened by NOAA, NASA, and the International Space Environment Services released their official prediction for solar cycle 25. They had analysed decades of historical data, consulted nearly 50 distinct forecasting models from research groups around the world, and applied every sophisticated technique available to modern heliophysics. Their conclusion was delivered with the careful confidence that comes from rigorous scientific process. Solar cycle 25 would be weak, similar in strength to solar cycle 24, which had been the weakest cycle in a century. The peak would arrive in July 2025, with a maximum smoothed sunspot number of 115, plus or minus 10. The cycle would represent a continuation of the declining trend in solar activity that had characterized the previous 4 cycles, a long term, weakening that some researchers interpreted as the Sun entering a grand solar minimum period similar to the Maunder minimum of the 17th century. It was a reasonable prediction, grounded in solid methodology and supported by the majority of the scientific community. And it was wrong, spectacularly, comprehensively wrong. By January 20th, 2023, just 3 years into the cycle, Solar Cycle 25 had already exceeded the total sunspot count that Cycle 24 had achieved at the same point in its development. Not by a small margin, by 12%. The Sun was producing more spots, more flares, more energetic events than any of the prediction models had anticipated. Something was happening that the models did not account for. Throughout 2023, sunspot numbers continued to climb at a rate that diverged increasingly from the predicted curve. By October of that year, NOAA's Space Weather Prediction Center took the unusual step of issuing a revised forecast, essentially admitting that the original prediction was no longer reliable. The new forecast called for solar maximum to occur between January and October 2024, significantly earlier than the July 2025 prediction, with a peak sunspot number between 137 and 173. That revision was released in October 2023. By August 2024, Solar Cycle 25 had already exceeded even the revised prediction, hitting a 13-month smoothed monthly value of 156.7 sunspots. The original prediction of 115 had been shattered. The cycle was not weak. It was not following the declining trend. It was strong, active, and accelerating faster than anyone had anticipated. On October 15th, 2024, NASA and NOAA held a joint press conference to announce what solar physicists had been quietly acknowledging for months. Solar Cycle 25 had reached solar maximum. The Sun was at the peak of its 11-year cycle, and it had gotten there earlier and stronger than predicted. But here is the truly fascinating part, the detail that reveals just how complex and poorly understood solar dynamics really are. We do not actually know when solar maximum occurred. We know it has occurred, past tense, but we cannot pinpoint the month or even the season with certainty. This seems absurd at first. We have satellites monitoring the Sun continuously, ground-based observatories tracking every sunspot, sophisticated instruments measuring solar radiation across the entire electromagnetic spectrum. How can we not know when the peak happened? The answer lies in the nature of what we're trying to measure. Solar maximum is not a specific moment. It is not like the summit of a mountain, a single point you reach and then descend from. It is more like a plateau, a broad region of elevated activity that can last for months or even years, with multiple peaks and valleys within that elevated period. The official determination of solar maximum requires looking backward, identifying the month with the highest smoothed sunspot number, and confirming that subsequent months show a consistent decline. You need about 6 months of post-peak data to be confident you have actually passed the maximum and are not just in a temporary dip before another surge. This means that in October 2024, when NASA and NOAA announced we'd reached solar maximum, they were making an educated guess based on the shape of the activity curve up to that point. The actual peak month might have been August. It might have been September. It might not happen until January 2025. And there is another complication, one that makes the determination even more uncertain. Solar cycles can have double peaks. This is not a rare anomaly. It is a documented pattern that has appeared in multiple historical cycles. Solar Cycle 24, the previous cycle, exhibited 2 distinct peaks, one in 2012 and a second, slightly lower one in 2014. The smoothed sunspot curve showed a clear inflection between them, a rise and fall and rise again pattern that complicated the determination of the true maximum. Some researchers analysing Solar Cycle 25 data have suggested that we have already seen evidence of a double peak structure. There was a significant rise in sunspot numbers during 2023, followed by a plateau and slight decline, then another surge in mid-2024 that produced the August peak of 156.7. The question is whether we are now in a declining phase that will lead into the next solar minimum, or whether we are in the valley between two peaks, with another surge still to come. If the latter is true, then solar maximum is not behind us. It is still ahead. This uncertainty has profound implications for space weather forecasting and risk assessment. If we are past the peak, then the frequency and intensity of major solar events should begin to decline over the next year or two. The probability of another May 2024 level geomagnetic storm decreases with each passing month. Infrastructure managers, satellite operators, and power grid controllers can begin to relax slightly, knowing that the most dangerous period has passed. But if we are between peaks, if the sun has another surge of activity still building, then we need to remain at high alert for potentially another year or more. The most intense geomagnetic storms of the cycle might not have happened yet, and this brings us back to AR4294 and its companion regions, because their appearance and behaviour provide clues about which scenario is more likely. Sunspot clusters of this size and magnetic complexity typically appear during the rising phase of a solar cycle or near solar maximum. They are less common during the declining phase, though not impossible. The fact that AR4294 emerged in late November, early December 2025, more than a year after the August 2024 peak, suggests one of two possibilities. Either this is a late-cycle monster, a final burst of activity before the sun settles into its declining phase, or this is evidence that we have not yet reached the true peak, that the August 2024 numbers were just the first summit of a double-peak structure. The magnetic configuration of AR4294 leans toward the second interpretation. Beta-gamma-delta complexity is a hallmark of highly active periods. It requires specific conditions in the sun's interior, a particular alignment of subsurface flows and magnetic field generation mechanisms that tend to occur when the solar dynamo is operating at or near maximum efficiency. Seeing this level of complexity emerge in late 2025, if we were truly in a declining phase, would be unusual though not unprecedented. There is another piece of evidence worth considering, something that has not received much attention in the mainstream coverage, but that solar physicists have been discussing with increasing interest. In July 2024, researchers at the University of Birmingham announced that they had detected the first signs of solar cycle 26 beginning, even though cycle 25 is not expected to end until around 2030. They were using helioseismic data, measurements of how the sun's interior rotates, to track something called solar torsional oscillation. This is a pattern of faster and slower rotating bands that migrates through the sun's convective zone during each cycle, and it has proven to be a reliable predictor of future solar activity. The Birmingham researchers found that the characteristic pattern that precedes a new solar cycle had already appeared in the data about 6 years before cycle 26 is officially scheduled to begin. This early appearance suggests that the sun's magnetic dynamo is more active, more energetic than the standard models predict. It suggests that cycle 26 might be strong, and that the transition between cycle 25 and 26 might be less smooth than usual. What does this mean for the next few years? One interpretation is that we are entering a period of sustained high solar activity that will extend well beyond the normal duration of solar maximum. Instead of a clean peak followed by a gradual decline, we might see a prolonged plateau with multiple peaks, ongoing production of large complex active regions, and a sustained elevated risk of major geomagnetic storms. This would be consistent with what we saw during the last true grand solar maximum, the period from the 1940s through the 1990s, when the sun was exceptionally active cycle after cycle. During that period, the transitions between cycles were less distinct. The valleys between peaks were shallower, and the overall level of solar activity remained elevated for decades. If we are entering a similar period now after several weak cycles, then everything we have been saying about space weather risk needs to be recalibrated. The threat is not a single Carrington-level event that might or might not happen in the next year. The threat is a sustained period of elevated risk, a multi-year window during which multiple major storms could occur, each one testing our technological infrastructure, each one with the potential to cause significant disruption. And here is the uncomfortable reality that nobody in the space weather community wants to say out loud, but that everyone is thinking. We're not ready for sustained high activity. Our preparedness measures, our contingency plans, our infrastructure hardening efforts, all of these are designed around the assumption of occasional storms separated by long periods of quiet. We can handle a May 2024 level event once every few years. We can absorb the disruption, repair the damage, and move on. But if we start seeing major storms every few months, if the G4 and G5 events become routine rather than exceptional, then the cumulative damage and the economic impact begin to compound in ways that are very difficult to manage. Power transformers that are stressed by one geomagnetic storm become more vulnerable to damage from the next one. Satellite components that are degraded by one radiation storm have less margin for surviving another. GPS systems that are repeatedly disrupted lose their reliability, and users begin to lose trust in them, which has cascading effects across agriculture, transportation, and countless other sectors that have become dependent on precision navigation. The May 2024 storm caused an estimated $500 million in damage to the agriculture sector alone, primarily through disruption of GPS-guided planting equipment. Farmers who rely on centimetre-level precision for seed placement and fertilizer application found their systems unusable for days during the critical planting season. Some were able to continue working with reduced precision. Others had to halt operations entirely. The lost productivity and reduced crop yields from that single event are still being calculated. Now imagine that happening 3 or 4 times per year for several years running. The economic impact stops being a one-time shock that the system can absorb and becomes a structural problem that requires fundamental changes in how we operate our technological infrastructure. This is not doom-mongering. This is risk assessment based on the possibility that the Sun is more active than we predicted, that solar maximum might extend longer than expected, and that we might be looking at several more years of elevated space weather risk, rather than the single peak and decline that the standard model suggests. AR4294 is a test case. Not the only test, but an important one. How this cluster behaves over the next few weeks as it transits across the Earth-facing solar disk, how many more X-class flares it produces, how many Earth-directed CMEs it launches, all of this will provide data points that help us understand whether we are past the peak or still climbing toward it. And the Sun is not giving us clear answers. Since rotating into view, AR4294 has been active but not explosively so. Multiple M-class flares, a few X-class events, several CMEs with varying degrees of Earth alignment. It is behaving exactly like a large complex active region should behave during solar maximum, which tells us nothing definitive about whether the maximum is past or ongoing. So we wait, we watch, we monitor the sunspot numbers month by month, looking for the consistent decline that will confirm we have passed the peak. We track the emergence of new active regions, analysing their size and complexity for signs of whether the solar dynamo is ramping up or winding down. We study the helioseismic data, searching for patterns that might give us advance warning of what the next cycle will bring. And while we wait, we hope that our luck holds, that the big one does not arrive before we have finished implementing all the infrastructure improvements that we know we need but have not yet completed. We hope that when the next Carrington scale event finally comes, whenever that might be, we will be ready. But hope is not a strategy, and readiness is not a binary state. We are more prepared than we were 5 years ago. We are less prepared than we need to be. And the Sun, as AR4294 demonstrates, does not care about our preparation timeline. When the grid goes dark, the May storm nobody saw coming. May 10th, 2024, began as an ordinary Friday for most of the world. But by midday, something extraordinary was happening. Social media erupted with photographs of auroras visible from places that never see them. Mexico City, northern India, Morocco, Perth, Australia. The northern lights had descended to latitudes where they appear perhaps once per century, painting skies in shades of crimson and green that startled people who had no context for what they were witnessing. It was the first G5 geomagnetic storm to strike Earth in over 20 years, and it caught almost everyone unprepared. The storm originated from active region 3664, a massive sunspot cluster that had appeared on the Sun's Earth-facing hemisphere in early May. Over the span of just 6 days, from May 6th through May 11th, AR4694 produced 12 X-class flares. 12. That is nearly unprecedented concentration of powerful eruptions from a single active region. Each X-class flare represented a massive release of energy, and most of them launched coronal mass ejections. But the real danger came from the timing. When multiple CMEs are launched in rapid succession from the same general location on the Sun, they do not travel through space as isolated bubbles. They interact. The faster CMEs catch up to the slower ones, creating compression zones where the plasma density and magnetic field strength are dramatically amplified. These merged structures, sometimes called CME cannibalization events, can produce geomagnetic effects far more severe than the sum of their individual components. That is what hit Earth on May 10th. The first CME arrived around 12:30 p.m. UTC, driving geomagnetic activity to G3 levels within hours. That alone would have been noteworthy. G3 storms are classified as strong, capable of causing voltage irregularities in power systems and requiring some satellite operators to take corrective actions. But it was just the opening salvo. Over the next 12 hours, 4 more CMEs arrived in sequence, each one merging with the disturbed magnetosphere created by the previous arrivals, each one pushing the geomagnetic indices higher. By late evening UTC, the storm had escalated to G5, the extreme category, and conditions remained at or near that level for over 48 hours. NOAA's Space Weather Prediction Center had issued warnings days in advance. They had tracked the emergence of AR4694, monitored its prolific flare production, modelled the trajectories of the CMEs. The forecasters knew a significant storm was coming. What they did not anticipate was the magnitude. The forecast models, even the sophisticated ones that account for CME interactions, predicted a G3 storm, possibly escalating to G4 if conditions aligned unfavourably. They were off by a full category. In the 5-level scale of geomagnetic storms, being wrong by one category means underestimating the severity by roughly an order of magnitude. Why the miss? Partly it is the sheer complexity of the physics involved. CME propagation through the interplanetary medium depends on factors that are difficult to measure and harder to predict. The density and velocity of the ambient solar wind, the orientation and strength of the interplanetary magnetic field, the precise trajectory and magnetic configuration of each CME, all of these variables interact in nonlinear ways that make deterministic prediction essentially impossible beyond rough approximations. But there is another factor, one that has become increasingly apparent as solar cycle 25 has ramped up. The Sun's behaviour during this cycle has consistently surprised us. Events that should be moderate turn out to be severe. Regions that look manageable suddenly explode with activity. The statistical relationships that were derived from decades of observations during previous cycles are not holding as reliably for cycle 25. It is as if the Sun is playing by slightly different rules, and we have not yet figured out what those rules are. The impacts of the May storm were widespread and varied. In the agriculture sector, as mentioned earlier, GPS-guided equipment became unreliable or completely non-functional. Tractors equipped with auto-steer systems that depend on centimetre-level positioning accuracy found themselves drifting off course or unable to establish position locks at all. During planting season, when timing is critical and every day of delay can impact yield, this disruption cascaded through the entire supply chain. One farmer in Iowa, interviewed for a local news report, described watching his $500,000 planter come to a complete stop in the middle of a field because it could not determine where it was. The GPS constellation was still broadcasting, but the signals were being refracted and scattered by the disturbed ionosphere to such a degree that the receiver could not resolve a stable position solution. He had to manually switch to conventional steering and complete the field at significantly reduced precision, knowing that the uneven seed spacing would likely cost him thousands of dollars in reduced yield come harvest time. Multiply that by hundreds of farmers across the Midwest experiencing similar problems, and you begin to understand how a geomagnetic storm translates into economic damage that has nothing to do with damaged satellites or power grid failures. Aviation was similarly affected. Commercial airlines that fly polar or high-latitude routes had to reroute to avoid regions where high-frequency radio communication was blacked out. The ionospheric disruption made it impossible for pilots to establish reliable contact with air traffic control using the standard HF bands. Satellite communication remained functional, but regulations require backup communication methods to be available, and when HF is unavailable, the approved flight paths change. A transatlantic flight from New York to London that would normally route over Greenland was diverted south, adding nearly 30 minutes to the flight time and burning hundreds of additional gallons of fuel. That flight was not unique. Dozens of flights across the North Atlantic and Arctic routes were similarly affected over the 3-day duration of the storm. The added fuel costs alone ran into millions of dollars, not counting the passenger delays and logistical complications. Power grids experienced voltage fluctuations as geomagnetically induced currents flowed through long-distance transmission lines. These are not the sudden catastrophic failures that make headlines. They are subtle perturbations, barely noticeable to end users, but potentially damaging to sensitive equipment like high-voltage transformers. A transformer that experiences repeated stress from geomagnetically induced currents has its operational lifetime shortened. Insulation degrades faster. Internal components experience thermal cycling that can lead to eventual failure. In Sweden, grid operators reported having to temporarily disconnect certain transmission lines to prevent equipment damage. In South Africa, one transformer suffered measurable degradation and had to be taken offline for inspection. These were not failures in the sense of causing blackouts, but they were near misses, warnings of what could happen if the storm had been slightly stronger or lasted slightly longer. Satellites in low Earth orbit experienced increased drag as the upper atmosphere heated and expanded. This is a predictable consequence of geomagnetic storms. Solar energy pumped into the ionosphere and thermosphere increases the temperature of those layers, which causes them to expand outward. Satellites that normally orbit in a near vacuum suddenly find themselves flying through a denser medium which slows them down. A satellite that is slowing down is losing altitude. If operators do not perform corrective burns to boost it back to its proper orbit, it will eventually re-enter the atmosphere and burn up. During a major geomagnetic storm, satellite operators have to decide whether to expend precious fuel for orbital adjustments or accept temporary altitude loss and deal with it later. For some satellites, especially older ones low on fuel, this decision can determine whether they survive or not. NOAA, the organization responsible for tracking all objects in Earth orbit, temporarily lost accurate position data on hundreds of satellites. The atmospheric drag changed their orbits faster than the tracking models could update. For several days, the orbital catalogue was degraded, which meant that collision avoidance calculations were less reliable. Satellite operators had to make decisions about maneuvering based on incomplete information, knowing that 2 satellites whose paths appeared safe might actually be on a collision course due to unpredicted orbital changes. This is the hidden cost of space weather that does not make the news. No satellites collided during the May storm, no catastrophic debris-generating crashes occurred, but the risk was elevated, the operators were stressed, and the margin for error was reduced. And if the storm had lasted another few days, if the atmospheric heating had been even more intense, we might have seen very different outcomes. But perhaps the most concerning aspect of the May event was how it revealed gaps in our infrastructure resilience that we thought we had addressed. After the Halloween storms of October 2003, which included an X-28 flare and multiple severe geomagnetic storms, there was widespread recognition that critical infrastructure needed better protection against space weather. Power utilities installed monitoring equipment and developed protocols for managing geomagnetically induced currents. Satellite manufacturers implemented additional radiation shielding and redundant systems. GPS receiver designs were improved to handle ionospheric disruption more gracefully. 20 years of preparation, billions of dollars invested in hardening and redundancy, and the May 2024 storm still caused $500 million in agricultural losses, forced dozens of flight diversions, stressed power grids across multiple continents, and created orbital tracking uncertainties that raised collision risks. We are better prepared than we were, but better prepared is not the same as adequately prepared. The reality check came in the weeks after the storm, as damage assessments were completed and after-action reports were compiled. NOAA published an analysis noting that if the preparedness actions had not been in place, if the advance warnings had not been heeded, if the mitigation measures had not been executed, the storm could have been much more consequential, potentially an order of magnitude more damaging, so we survived. We took the hit, absorbed the impacts, and proved that our preparation efforts had value. But the phrasing in that NOAA report is telling. Could have been much more consequential. Not would have been. Could have been. Because we got somewhat lucky, the May storm was severe, but it was not worst case. The magnetic field configuration of the CMEs, when they arrived at Earth, happened to be oriented in a way that did not produce the absolute maximum coupling with our magnetosphere. The BES component of the interplanetary magnetic field, which determines how effectively the solar plasma can transfer energy into Earth's system, was moderately negative but not extremely so. If the BES had been more strongly negative, if the CMEs had hit when our magnetosphere was already stressed from previous activity, if the sequence of arrivals had been slightly different, we could easily have seen a G5 storm that caused actual grid failures, destroyed multiple satellites, and generated economic losses measured in tens of billions rather than hundreds of millions. The May event was a warning shot. It showed us that our preparation efforts are necessary but not sufficient. It demonstrated that even with days of advance warning, even with every mitigation measure in our playbook being executed, we still experience significant impacts, and it revealed that our understanding of how to predict storm severity is still inadequate. The forecast model said G3, maybe G4. Reality delivered sustained G5. That gap between prediction and outcome is not acceptable when the systems at risk include continental power grids, global navigation infrastructure, and the satellite networks that underpin modern communication and commerce. Since May, there has been intense activity in the space weather research community to understand what the models missed and how to improve them. Some of the focus has been on better characterizing CME magnetic field structures, which are extremely difficult to measure remotely but critically important for predicting storm intensity. Other work has concentrated on improving the models that simulate CME propagation through interplanetary space and interaction with Earth's magnetosphere. But there is also a growing recognition that no amount of model improvement is going to give us deterministic predictions. The system is too complex, too chaotic, too dependent on initial conditions that we cannot measure with sufficient precision. The best we can hope for is probabilistic forecasting. This CME has a 30% chance of causing a G4 storm and a 10% chance of G5. Which brings us back to December 2025 and the current situation with AR4294. We have multiple CMEs in flight, launched from a Sunspot complex that is 90% the size of the Carrington Event cluster, during a solar maximum that has already proven more intense than predicted. The forecast models are saying G3 with possible escalation to G4. Should we believe them? Or should we remember May and prepare for the possibility that reality might exceed predictions by a full category again? 90% to apocalypse. Measuring the unmeasurable. There is a deceptive simplicity to the 90% number. AR4294 is 90% the size of the Carrington Event Sunspot. It sounds precise, scientific, a straightforward comparison that tells you exactly what you are dealing with. But size is only one variable in an equation with dozens of terms, most of which we cannot measure directly, and some of which we barely understand. The 90% figure tells you something important about the potential of AR4294, but it tells you almost nothing about the probability. Let me explain why that distinction matters, and why the science of predicting solar eruptions is far more art than equation. Richard Carrington's observations on September 1st, 1859, were meticulous. He sketched the sunspot group he was observing, recording its size, structure, and position on the solar disk with the precision that characterized Victorian-era astronomy. Those sketches survived, and modern researchers have used them to reconstruct the physical dimensions of the Carrington sunspot with reasonable accuracy. The cluster measured approximately 1,600 million square kilometers in total area, accounting for all the individual spots in the penumbral region surrounding them. AR4294, based on high-resolution imagery from the Solar Dynamics Observatory and careful pixel counting, measures approximately 1,400 million square kilometers. 90% is not an approximation. It is an actual measurement, accurate to within the margins of uncertainty inherent in comparing historical drawings to modern digital images. So the size comparison is solid. What about everything else? The Carrington Event flare was estimated to be an X45, based on reconstruction using modern space weather models applied to the magnetometer records that survived from that era. Those magnetometers were not designed to measure solar storms. They were designed to study Earth's background magnetic field. When the Carrington storm hit, the needle swung so far off scale that the instruments basically flatlined for hours. The researchers doing the reconstruction has had to work backward from the known effects, the telegraph disruptions, the aurora observations, the duration and intensity of the geomagnetic disturbance, to estimate what class of solar flare could have produced those outcomes. X45 is their best estimate, but the uncertainty range on that number is huge. It could have been X30, it could have been X60. We will never know with precision. Now consider what we can measure about AR4294. We have continuous high-resolution observations across multiple wavelengths. We have magnetograms showing the detailed structure of the magnetic fields threading through the sunspot. We have spectroscopic data revealing the temperature, density, and velocity of plasma at different heights in the solar atmosphere above the active region. We have helioseismic measurements probing the subsurface structure and flows beneath the visible surface. It is an embarrassment of riches compared to what Carrington had available. And yet, with all this data, with all our sophisticated instruments and computer models, we still cannot tell you whether AR4294 will produce an X45 flare. We cannot even tell you with confidence whether it will produce any X-class flares at all. The problem is magnetic complexity. Solar flares are powered by the release of energy stored in twisted magnetic fields. The more twisted the fields, the more energy is stored, the more powerful the potential flare. But measuring the degree of twist, the magnetic topology, is extraordinarily difficult because we can only observe the magnetic field at the visible surface of the Sun. Below the surface, where the twisting originates, we have to infer the structure from indirect observations. Above the surface, in the corona where the flares actually erupt, the magnetic fields are so complex and dynamic that even our best models struggle to represent them accurately. The beta-gamma-delta classification that AR4294 has been assigned is a rough descriptor, not a precise measurement. It tells you that opposite polarity magnetic fields are close together, that there is significant shear between them, that delta configurations, which are particularly unstable arrangements, are present in the magnetic structure. All of these characteristics increase flare probability and potential magnitude, but they do not guarantee anything. Some beta-gamma-delta regions produce multiple X-class flares. Others produce nothing stronger than M-class events before decaying and disappearing. The magnetic configuration is a necessary condition for major flares, but it is not sufficient. What else matters? The history of the active region, how long it has been on the visible disk, how rapidly it developed, whether it is growing or decaying, the rate of magnetic flux emergence, which is a measure of how much new magnetic field is being brought up from the solar interior into the active region. AR4294 showed rapid emergence and development, going from barely visible to massive in less than 48 hours. That is a sign of vigorous activity, suggesting that the subsurface dynamics feeding the region are strong. But rapid development can also mean rapid decay. Some of the most spectacular active regions in recorded history flared intensely for a few days and then collapsed, their magnetic structure untwisting and dispersing before they could produce the truly catastrophic events they seemed capable of. You also have to consider the active region's position on the solar disk. A flare from a sunspot near the center of the disk is more likely to produce a geo-effective CME, one that hits Earth, than a flare from near the limb where the geometry sends most of the ejector off to the side. Carrington observed his sunspot near the center of the disk. The flare he witnessed erupted when the active region was ideally positioned to blast its fury directly at Earth. AR4294 rotated into view from the eastern limb, meaning it started its transit across the Earth-facing hemisphere at a relatively oblique angle for Earth impacts. By the time it reached the central meridian, the optimal position for geo-effective events, it had already produced several flares and CMEs. Did those earlier eruptions release enough magnetic energy to reduce the probability of a major event later? or did they simply reflect ongoing build-up, with the biggest blast still waiting to happen? These are not rhetorical questions. They are literally questions that solar physicists ask when assessing the threat from an active region, and the honest answer to most of them is we do not know for certain. Then, there is the question of magnetic field orientation in the CME itself. This is arguably the most important factor for determining geomagnetic storm severity, and it is essentially unpredictable more than a few hours before the CME arrives at Earth. When a CME is launched from the Sun, it carries with it a piece of the solar magnetic field, frozen into the plasma cloud. That magnetic field has a direction, an orientation defined by where the field lines point. If the CME reaches Earth and its magnetic field happens to be oriented southward, opposite to Earth's field, then the two fields can reconnect, allowing energy and particles to flow from the solar wind into the magnetosphere. This creates geomagnetic storms. The stronger the southward component, the more intense the reconnection, the more severe the storm. But if the CME's field is oriented northward, aligned with Earth's field, then reconnection is minimal and the geomagnetic effects are weak, even if the CME itself is massive and energetic. We cannot predict the magnetic field orientation of a CME by looking at the flare that produced it. The field gets twisted and reoriented during the eruption and the subsequent propagation through space. It can interact with other CMEs, with correlating interaction regions from coronal holes, with the general structure of the interplanetary magnetic field. By the time it reaches Earth, the orientation can be completely different from what it was when it left the Sun. The only way to measure it is with spacecraft positioned upstream from Earth, like the Dieskova satellite at the L1 Lagrange point. Dieskova measures the solar wind in real time, including the strength and direction of the embedded magnetic field, and transmits that data back to Earth. This gives us about 30 to 90 minutes of warning before a CME hits, which is just barely enough time to send alerts to power grid operators and satellite controllers, but not nearly enough time to implement major protective measures. So the sequence goes like this. We see a large complex active region like AR4294. We measure its size and magnetic configuration. We classify it as high threat. We watch it carefully and observe the flares it produces. We track the CMEs launched by those flares and model their trajectories. We predict that a geomagnetic storm is likely when the CMEs arrive at Earth, but we cannot predict the storm's intensity with confidence until the CME actually arrives and Dieskova measures its magnetic field, at which point we have less than 2 hours to react. This is not a failure of science. This is recognition of the inherent limits of predictability in a chaotic system. Chaos theory tells us that certain types of systems are fundamentally unpredictable beyond short time horizons, not because our measurements are imprecise or our models are inadequate, but because tiny differences in initial conditions get amplified exponentially over time. Weather is a classic example. We can predict tomorrow's weather fairly well, next week's weather roughly, but 2 weeks out the predictions are barely better than random guessing, no matter how good our satellites and computer models become. Solar flare prediction appears to have similar fundamental limits. We can identify high-threat regions. We can say that a major flare is possible, even likely within a certain time window. But pinning down when it will happen, how strong it will be, and where exactly the ejected material will go requires a level of precision in measuring initial conditions that may be physically impossible to achieve. And yet, we keep trying, because the stakes are high enough that even marginal improvements in prediction accuracy have enormous value. If we could predict a G5 geomagnetic storm 12 hours in advance instead of 2 hours, power grid operators could preemptively reduce loads, reconfigure transmission paths, and disconnect vulnerable transformers. The difference between 2 hours and 12 hours warning could be the difference between controlled, rolling blackouts that last a few hours and uncontrolled cascading failures that leave entire regions without power for weeks. If we could reliably identify which CMEs will have strongly southward magnetic fields, we could focus our preparation efforts on those events and avoid crying wolf about CMEs that look dangerous but turn out to be geomagnetically benign. The economic cost of false alarms, of unnecessarily diverting flights or shutting down satellite operations, is not trivial. Better discrimination between real threats and false positives would allow resources to be allocated more efficiently. So the research continues. new instruments are being developed to measure coronal magnetic fields more directly. Machine learning algorithms are being trained on decades of solar observations to identify subtle patterns that human analysts might miss. Improved models of CME propagation are being run on increasingly powerful supercomputers, simulating the complex dynamics of plasma clouds moving through the variable solar wind. But we need to be realistic about the limits. AR4294 is 90% the size of the Carrington Sunspot. That tells us it has enormous potential. It does not tell us what will actually happen. And that gap between potential and outcome is where uncertainty lives, where chaos operates, where our most sophisticated models fail to give us the answers we desperately want. The sun does not care about our models or our need for certainty. It will do what its internal dynamics compel it to do, following laws of physics that we understand in principle, but cannot predict in detail. AR4294 will either produce a historic flare or it will not. It will either launch a Carrington-scale CME at Earth, or it will not. And we will not know which outcome occurs until it happens, until the photons and particles are already on their way, and our window for preparation has closed to a narrow slice of time measured in minutes and hours. That is the reality of space weather forecasting in 2025. We are better than we were. We are not as good as we need to be. And the sun, indifferent to our limitations, continues to surprise us with events that exceed our predictions and challenge our assumptions about what is possible. AR4294 is a test of those assumptions, a reminder that 90% similarity in one measurement does not translate to 90% predictability in outcomes. It is a challenge to our models, our preparation, and our ability to respond to threats we can see coming, but cannot quantify with the precision that modern society expects from its scientific institutions. The cluster is still there, still active, still rotating across the Earth-facing solar disk, and every few hours we check the latest data, looking for signs of what might come next, knowing that when it does come, we will have little time to react and even less certainty about whether our reactions will be adequate. The double peak anomaly, why the sun refuses to follow the rules. Solar cycle, 24 peaked twice, once in 2012, then again in 2014. The two peaks were separated by nearly 2 years of moderately elevated activity, creating a broad plateau rather than the sharp mountain profile that textbooks show for idealized solar cycles. At the time, this was considered unusual but not unprecedented. Historical data showed that double peaks appear in roughly 40% of solar cycles, making them common enough to be expected but rare enough that each occurrence still requires explanation. Solar cycle 25 appears to be following the same pattern, possibly. The uncertainty in that simple statement reveals how much we still do not understand about the most important star in our sky. The mechanism behind double peaks involves the sun's two hemispheres operating on slightly different schedules. The sun is not a solid body, it is a ball of plasma rotating differentially, meaning different latitudes spin at different rates. The equator completes a rotation in about 25 days. The polar regions take nearly 36 days. This differential rotation, combined with the sun's internal magnetic dynamo, drives the solar cycle. But the dynamo does not operate identically in both hemispheres. The northern and southern hemispheres of the sun have independent magnetic cycles that are coupled but not perfectly synchronized. Sometimes one hemisphere reaches its activity peak before the other. When the lag between hemispheres is small, you get a single sharp peak as both hemispheres contribute to a concentrated burst of activity. When the lag is large, you get two distinct peaks as each hemisphere maximizes in turn. Solar cycle 24 showed a particularly pronounced hemispheric asymmetry. The northern hemisphere peaked in 2012 with a smooth sunspot number around 115. The southern hemisphere was quiet during that time, still in its rising phase. Then the north declined while the south ramped up, producing a second peak in 2014 that was slightly lower than the first at around 110. The total cycle, measured from minimum to minimum, lasted 11 years, which is average, but the maximum phase, the period of elevated activity, extended for nearly 4 years from the first northern peak to the final decline of the southern peak. This prolonged maximum created an extended window of elevated space weather risk, which is one reason why the 2012 to 2015 period saw several significant geomagnetic storms, despite cycle 24 being overall one of the weakest cycles on record. Now look at solar cycle 25. In 2023, the Northern Hemisphere showed strong activity with numerous large sunspot groups and elevated flare production. This created what appeared to be an early peak, well ahead of the predicted July 2025 maximum. Then in mid to late 2023, activity declined somewhat, leading some researchers to suggest that the Northern Hemisphere had peaked and we were entering a transitional phase. But then came 2024. The Southern Hemisphere erupted with a surge of activity that pushed the smooth sunspot numbers even higher than the 2023 values. The August 2024 peak of 156.7 was driven primarily by Southern Hemisphere sunspot groups, with the Northern Hemisphere contributing less than in the previous year. This looks like a classic double peak structure. Northern Hemisphere peaks first, then Southern. Except for one complicating factor, the timing does not quite fit the standard model. In solar cycle 24, the two peaks were separated by about 2 years. In cycle 25, the apparent peaks are separated by only about 1 year. That is a much shorter interval, suggesting either that the hemispheric lag is smaller this cycle, or that we are not actually looking at a double peak structure, but rather normal fluctuations within a prolonged single maximum. The difference matters enormously for forecasting what comes next. If we are seeing a true double peak with the Southern Hemisphere having reached its maximum in August 2024, then we should expect activity to decline over the next year or so as both hemispheres wind down towards solar minimum. The frequency of large sunspot groups should decrease. X-class flares should become less common. The risk of major geomagnetic storms should gradually diminish. But if the August 2024 peak was not the Southern Hemisphere maximum but rather an early surge, if the Southern Hemisphere is still ramping up toward a higher peak yet to come, then we might be looking at another year or even 2 of sustained elevated activity. More large complex regions like AR4294, more X-class flares, continued high risk of severe space weather events. How do we tell which scenario is correct? Ideally, we would wait 6 months, see if activity continues to decline, and make the determination retrospectively once we have enough data to be confident. But that is not very useful for planning purposes. Infrastructure managers and mission operators need to make decisions now about resource allocation, maintenance scheduling, and risk mitigation strategies. Those decisions depend critically on whether we are past the peak or still approaching it. Enter the helioseismology data. Helioseismology is the study of how sound waves propagate through the sun's interior. These waves, generated by turbulent convection in the outer layers, travel down through the solar plasma, bounce off density changes in the deep interior, and return to the surface where we can observe them as subtle oscillations. By analysing the frequencies and travel times of these waves, we can map the internal structure and rotation of the sun with remarkable precision. One particular pattern that helioseismologists track is the torsional oscillation, which is a band of faster than average rotation that migrates from mid-latitudes toward the equator during each solar cycle. This band is thought to be directly connected to the magnetic dynamo process that generates sunspots. When a new cycle begins, a new torsional oscillation band appears at high latitudes in both hemispheres and begins its journey toward the equator. The band reaches the equator around solar maximum, then dissipates as the cycle declines. But here is the fascinating part. The torsional oscillation for the next cycle begins before the current cycle ends. Researchers at the University of Birmingham announced in July 2024 that they had detected the first signs of the solar cycle 26 torsional band, even though cycle 25 is not expected to end until around 2030. The cycle 26 band appeared about 6 years ahead of schedule. This early appearance has several possible interpretations. One is that solar cycle 25 will be shorter than expected, ending sooner and transitioning to cycle 26 ahead of the standard 11-year timeline. This would be consistent with the pattern that strong cycles tend to be shorter than weak ones, and cycle 25 has proven to be stronger than predicted. Another interpretation is that the cycle 26 band appeared early because the sun's dynamo is operating at higher intensity than normal, essentially running ahead of schedule. This could mean that not only is cycle 25 stronger than expected, But cycle 26 will be strong as well, potentially ushering in a new grand solar maximum period after several decades of relatively weak cycles. A third interpretation involves the complex interactions between the two hemispheres. The cycle 26 torsional band appeared first in the northern hemisphere, which is the same hemisphere that peaked first in cycle 25. This could indicate that the northern hemisphere is essentially already starting to transition toward the next cycle, while the southern hemisphere is still finishing its cycle 25 maximum. If true, this would suggest a very unusual and potentially destabilizing level of hemispheric asynchrony. Destabilizing in the sense that the two hemispheres competing at different phases of their cycles could create unusual magnetic configurations that produce unexpected solar activity. Some of the most intense solar events in the historical record occurred during periods when the hemispheres were maximally out of phase, possibly because the competing magnetic structures created zones of intense instability. AR4294 might be a manifestation of exactly this kind of hemispheric competition. The cluster's extreme size and magnetic complexity could reflect unusual subsurface dynamics driven by the overlapping cycles. If the northern hemisphere is already starting to wind down towards solar minimum, while the southern hemisphere is still at or near its maximum, the interaction between these opposing trends could be creating conditions that favor the emergence of monster active regions. This is speculative, admittedly, but it is speculation grounded in observational data and theoretical understanding of how the solar dynamo operates, and it is being taken seriously by the research community because the alternative is to assume that AR4294 is just a random outlier, a statistical fluke with no deeper meaning. That might be true, but it would be unwise to bet our infrastructure resilience on that assumption. The double peak question also connects to broader concerns about long-term solar activity trends. For much of the 20th century, the sun was exceptionally active, producing strong solar cycles with high sunspot numbers and frequent major events. This period, sometimes called the modern maximum, lasted from roughly the 1940s through the 1990s. Solar physicists studying this period noted that cycles during the modern maximum showed less variability, shorter durations, and more consistent behavior than cycles during quieter periods. Then came solar cycle 23, which showed signs of decline. Cycle 24 was dramatically weaker, leading to widespread speculation that the sun was entering a new grand minimum similar to historical periods like the Maunder minimum or Dalton minimum, when solar activity nearly ceased for decades. But cycle 25 has contradicted that narrative. Instead of continuing the decline, it reversed course and came back strong. This reversal raises questions about whether we were ever really on track for a grand minimum, or whether the weak cycle 24 was just an anomaly, a temporary dip before activity resumed its long-term average. The double peak structure, if confirmed, might be part of the answer to these questions. Double peaks are associated with hemispheric asynchrony, which in turn is connected to the complex dynamics of the solar dynamo. During periods when the dynamo is transitioning between different modes of operation, when the magnetic field generation process is reconfiguring itself, you tend to see more irregular behavior, more double peaks, more cycle-to-cycle variability, more unpredictability. If the sun is currently in such a transitional phase, oscillating between grand minimum and grand maximum modes, trying to settle into a stable long-term pattern, then the next decade or two could be marked by continued unpredictability, cycles that exceed predictions, activity patterns that do not match historical norms, solar events that challenge our assumptions about what is possible. This is uncomfortable for a civilization that has become utterly dependent on technological systems vulnerable to space weather. We want the sun to be predictable. We want to know with confidence what the next cycle will bring so we can plan appropriately and allocate resources efficiently. But the sun appears to be in a phase where predictability is limited, where each cycle surprises us in different ways, where the only certainty is continued uncertainty. AR4294 in this context becomes more than just a single threat. It becomes a symbol of the challenge we face in trying to operate advanced technological civilization during a period of heightened and unpredictable solar activity. We know the sun is capable of producing Carrington scale events. We know our infrastructure is vulnerable, but we cannot say with confidence how probable such events are in the next year, the next cycle, or the next decade. because the Sun is not following the patterns we expect, and the models we have built on historical data are proving inadequate to predict the present. So we adapt. We improve our monitoring, we refine our models, we harden our infrastructure incrementally, one transformer at a time, one satellite design improvement at a time, one grid management protocol at a time. And we accept that living with a star that refuses to follow the rules means living with a level of risk that we can mitigate but never fully eliminate. The double peak is not just a scientific curiosity. It is a reminder that the Sun is a dynamic, complex, only partially understood system that will surprise us no matter how sophisticated our instruments become. And those surprises, like AR4294 rotating into view with 90% the size of the Carrington Sunspot, are moments when theory meets reality and we discover how much we still have to learn. 17.6 hours. The speed that changes everything. The coronal mass ejection that struck Earth on September 2nd, 1859, travelled 93 million miles in 17.6 hours. That works out to an average velocity of roughly 5 million miles per hour, or about 2,300 kilometers per second. It was extraordinarily fast, possibly the fastest CME transit ever recorded, though recorded is perhaps too strong a word for an event that occurred before we had instruments to measure such things directly. The speed was calculated backward from the timing. Carrington observed the solar flare at 11:18 am GMT on September 1st. The geomagnetic storm began on Earth approximately 17.6 hours later. The distance between the Sun and Earth is well established. Divide distance by time, you get velocity. Simple calculation, profound implications. Why does speed matter? Because it determines everything about how a CME interacts with Earth's magnetosphere. A typical CME travels at 300 to 500 kilometers per second. At that speed, the transit from Sun to Earth takes 2 to 4 days. This gives us multiple days of warning between when we observe the flare and CME launch and when the storm impacts Earth. Multiple days to issue alerts, brief operators, prepare contingency plans, reconfigure systems to be more resilient. A fast CME, travelling at 1,000 to 1,500 kilometers per second, covers the distance in less than 2 days. Warning time drops to 30 to 40 hours, still useful, but the margin for error in forecasting tightens considerably. If your trajectory prediction is off by a few degrees, the difference between a direct hit and a glancing blow becomes apparent only in the final hours before arrival. The Carrington CME at 2,300 kilometers per second gave Earth essentially no warning at all by modern standards. Even if Carrington had possessed the instruments and knowledge to understand what he was witnessing and transmit that information globally, the world would have had less than 18 hours to prepare. In 1859, with communication limited to telegraph speeds and no concept of space weather, those 18 hours were meaningless. But even today, with our satellite networks and instant global communication, 18 hours is barely enough time to implement meaningful protective measures for critical infrastructure. But here is the truly terrifying aspect of the Carrington CME speed. It was not just fast, it was accelerated. Normal CME propagation is fairly straightforward. The eruption launches a plasma bubble away from the Sun. That bubble expands and travels outward, gradually slowing down as it pushes through the ambient solar wind. By the time it reaches Earth, it has typically decelerated to a few hundred kilometers per second, less than its initial velocity. The interplanetary medium acts like a fluid resistance, drag that bleeds energy from the CME. But the Carrington CME did not slow down. Analysis of the historical record suggests it may have actually accelerated during its transit. How is that possible? Through a mechanism called CME cannibalization combined with solar wind clearing. Here is how it works. In late August 1859, the Sun produced a significant CME that was not directed at Earth, but that cleared out a large portion of the interplanetary space between Sun and Earth, essentially creating a low-density tunnel. Then came the Carrington eruption, launching its CME into that cleared region. With less ambient solar wind to push against, the Carrington CME encountered less resistance and maintained more of its initial velocity. But there is another factor. If multiple CMEs launch in sequence, and the later ones are faster than the earlier ones, the fast CMEs catch up to the slow ones. When they collide or merge, the combined structure can be accelerated by the compression and shock dynamics. It is like a multi-stage rocket, where each stage adds energy to the system. The evidence suggests that this is what happened in 1859. The August CME cleared the path. The Carrington CME followed, maintained its speed through the cleared region, and may have been further accelerated by interactions with residual plasma from the earlier eruption. By the time it reached Earth, it was travelling at velocities that exceeded anything in the modern observational record. Only one other event in recent times has shown comparable speeds. The July 2012 solar storm, which missed Earth by about 9 days of orbital position, produced a CME that reached velocities estimated at around 2,000 km per second. That event was studied intensively because it represented a near miss with a Carrington-scale impact. Had it occurred a week earlier, when Earth was in its path, we would have experienced the most severe geomagnetic storm in over a century. The July 2012 CME also showed evidence of acceleration through interaction with a preceding eruption. The Sun produced 2 CMEs within hours of each other, the second one faster than the first, and they merged during transit. The combined structure ploughed through space at speeds that shocked the researchers analysing the data. This pattern of back-to-back CMEs, with the later one being faster, and the two merging into an accelerated composite structure, is now recognised as the mechanism for producing extreme velocity events, and it is a pattern we need to watch for carefully during periods of high solar activity, because it can turn a moderate threat into an extreme one with very little warning. The current situation with AR4294 and its companion regions presents exactly this risk. We have multiple active regions in close proximity, each capable of producing CMEs. If they fire in sequence with the timing and geometry aligned properly, we could see another CME cannibalization event. A fast mover catching a slow mover, merging, accelerating, arriving at Earth with velocities and impact energies that exceed the predictions based on the individual eruptions. This is not just theoretical concern. It has happened. It happened in 1859. It happened in July 2012. It happens in miniature form fairly regularly during solar maximum, though most of those events do not produce extreme velocities because the timing and trajectory alignment are not quite right. But when the alignment is right, when multiple factors converge, you get something truly dangerous. You get a CME travelling so fast that it reaches Earth before we have time to fully implement protective measures, and because it is travelling so fast, because it has so much kinetic energy, the impact on the magnetosphere is proportionally more severe. The relationship between CME velocity and geomagnetic storm intensity is not linear, it is exponential. A CME moving at 500 km per second might produce a G1 or G2 storm. Double the velocity to 1,000 km per second, and you do not get a G2 or G3 storm. You get a G4 or G5 storm. The energy transfer scales with velocity squared, so doubling speed quadruples impact. The Carrington CME, at 2,300 km per second, was hitting Earth with approximately 16 times the kinetic energy of a typical CME moving at 575 km per second. 16 times. That is the difference between a nuisance event that causes minor disruptions and a civilization-scale threat that could bring down continental power grids. And here is the nightmare scenario that keeps space weather researchers awake at night. A Carrington velocity CME with a strongly southward magnetic field orientation. Because the two factors multiply. Velocity determines how much energy is delivered. Magnetic field orientation determines how efficiently that energy couples into the magnetosphere. Get both factors aligned for maximum impact, and you have an event that could exceed the Carrington storm in its effects on modern technological infrastructure. We came close to this scenario in May 2024. The CMEs that produced the G5 storm were moving at moderately fast velocities, around 800 to 1,000 km per second. Not extreme, but fast enough to produce significant impacts. The magnetic field orientation was moderately southward, enough to drive strong reconnection but not the worst-case alignment. If those CMEs had been moving at Carrington velocities, if the magnetic field had been more strongly southward, the May storm could have been far worse. The question now is whether AR4294 will produce such an event. We know the cluster is capable of powerful eruptions. We know it is magnetically complex enough to generate X-class flares. We know that it is positioned, along with its companion regions, in a configuration that could produce sequential CMEs if the flaring cascades across the multiple active regions. What we do not know is whether those CMEs, if they occur, will have the right timing and trajectories to produce a cannibalization event. Will they launch within hours of each other? Will the later ones be faster than the earlier ones? Will they be aimed closely enough at Earth that the merged structure hits us directly? These are questions that cannot be answered until the events actually happen. The initial velocity and trajectory of a CME can be estimated from coronagraph observations in the first few hours after launch, but the predictions have large uncertainties and can change as more data comes in. The possibility of mid-transit acceleration through interaction with other CMEs is even harder to predict because it depends on encountering structures in interplanetary space whose exact positions and properties are unknown. So we watch. We monitor every flare from AR4294 and its neighbours. We track every CME launch. We run ensemble models that explore a range of possible trajectories and interaction scenarios. And we hope that if the dangerous alignment does occur, if the pieces fall into place for a fast mover, we will see it coming, with enough time to at least get the word out to the operators who can implement emergency protective measures. 17.6 hours. That was the warning time in 1859, though it was useless because nobody understood what it meant. Today, with our knowledge and our systems, 17 hours would be just barely enough. Power grid controllers could begin load shedding procedures. Satellite operators could put spacecraft into safe modes. Airlines could ground polar flights. Critical infrastructure managers could activate their contingency plans. But it would be rushed. It would be chaotic. Some measures would not be fully implemented before the CME arrived. Some warnings would not reach all the necessary parties. Some systems would be caught unprepared because the people responsible for protecting them did not believe the warning was credible or underestimated the severity of what was coming. This is not speculation. This is what we learned from the May 2024 event. Despite days of advance warning, despite every effort to prepare, there were still surprises, still impacts that exceeded expectations, still vulnerabilities that were not adequately protected. And the May event gave us much more than 17 hours warning. A true Carrington velocity CME would compress that entire preparation timeline into less than a day. From first observation of the flare to arrival of the storm at Earth, 17 to 20 hours. And within that window, we have to detect the flare, analyze the CME, model its trajectory, determine the likely impact parameters, issue warnings through multiple channels, have those warnings received and understood by the relevant operators, and execute whatever protective measures are possible in the remaining time. It is doable. Barely. But there is no margin for error. No time for second guessing. No opportunity to wait for better data before making decisions. You see the eruption, you make your best estimate of the threat, and you act immediately because waiting for certainty means losing the opportunity to prepare. This is the reality of extreme space weather in the modern era. The same event that caused telegraph wires to spark in 1859 would today be a test of whether our technological civilization can respond fast enough to protect itself from its own vulnerabilities. Whether the 17.6 hours of warning that a Carrington velocity CME provides is sufficient to prevent widespread infrastructure damage. Whether the systems we have built to monitor and forecast space weather are robust enough to operate accurately under the pressure of a real crisis, with real consequences measured in trillions of dollars and potentially millions of lives disrupted. AR4294 is positioned to answer these questions. Not hypothetically, but actually. If it produces the right sequence of eruptions, if the geometry aligns, if the sun decides to remind us once again of its power, we will find out whether we are ready, and the answer will arrive in 17 hours or less. Beta Gamma Delta, decoding the magnetic signature of chaos. The magnetic classification system for sunspots was developed in the 1940s by astronomers trying to understand why some spots produced major flares while others remained quiet despite similar sizes. They discovered that the answer lay not in the visible structure of the sunspot, but in the hidden architecture of the magnetic fields threading through it. Over decades of observation and refinement, a classification scheme emerged that uses combinations of Greek letters to describe increasingly complex and unstable magnetic configurations: alpha, beta, gamma, delta. Each letter represents a step up in complexity, in the degree of magnetic entanglement, in the probability of violent reconfiguration. An alpha sunspot is simple, single polarity, unipolar. All the magnetic field lines emerging from the spot point in the same direction. These are usually small, isolated spots that form, live quietly for a few days, and decay without producing significant activity. Alpha spots might generate a few minor C-class flares at most. A beta configuration involves two spots of opposite polarity, a north and a south pole like a bar magnet lying flat on the solar surface. This is the basic structure of most sunspot groups. Magnetic field lines emerge from one spot, arch through the corona, and descend into the other spot. Beta regions can produce M-class flares when the field lines become stressed and break, but they typically lack the complexity needed for X-class events. Add gamma to beta, and you get beta-gamma, which means multiple spots of both polarities are present in a disordered arrangement. The simple dipole structure of a pure beta region is complicated by additional spots that create magnetic field lines crossing and intertwining. This increases the stored energy and the probability of powerful flares. Many X-class flares come from beta-gamma regions, but then there is delta, and delta changes everything. A delta configuration exists when opposite polarity umbras, the dark cores of sunspots, share a common penumbra. In simpler terms, you have north and south magnetic poles pressed so close together that their outer boundaries touch or overlap. This is an extremely unstable arrangement. It is like trying to force two powerful magnets together with their opposing poles facing each other. The magnetic tension is enormous. The field lines are twisted into configurations that cannot be sustained indefinitely. When a region has delta structure within an already complex beta-gamma arrangement, you get beta-gamma-delta, the highest complexity classification. These regions are capable of producing the most powerful flares and the most energetic CMEs. The Halloween storms of October 2003 came from a beta-gamma-delta region. The May 2024 superstorm originated from a beta-gamma-delta cluster, and AR4294 has been classified beta-gamma-delta since it rotated into view. But what does this actually mean in physical terms? What is happening beneath the visible surface to create these dangerous configurations? The Sun's magnetic field is generated by a dynamo process operating deep in the solar interior. Plasma motions, particularly the differential rotation, and convective flows, stretch and twist magnetic field lines. These tangled fields rise buoyantly toward the surface like twisted ropes of magnetic flux. When they emerge through the photosphere, they create sunspots at the points where the field lines penetrate the surface. In a simple case, a single rope of magnetic flux emerges, forming a dipole pair with one spot where the field lines exit the surface and another spot where they return. But the process is rarely that clean. Multiple flux ropes can emerge in close proximity. They can have different orientations, different twist rates, different emergence timings. When they push through the surface in a crowded region, they interact, interfere, create complex structures that are not magnetically stable. A delta configuration typically forms when two flux ropes of opposite polarity emerge so close together that they cannot separate cleanly. Their magnetic fields oppose each other, creating a zone of extreme shear where field lines from one rope press against field lines from the other. This shear region is where the energy gets stored, concentrated in a narrow boundary between warring magnetic structures. Think of it like a geological fault line. On one side, rock is being pushed east. On the other side, rock is being pushed west. The boundary between them is locked by friction, unable to move despite the immense forces acting on it. Stress builds over time until it exceeds the strength of the lock, and the fault ruptures in an earthquake that releases decades of accumulated energy in seconds. Magnetic shear works similarly. The opposing forces build stress in the magnetic field. The field lines twist and distort but cannot break because the plasma is highly conductive and the field is frozen into it. Energy accumulates. And then, when some threshold is crossed, when the twist becomes too extreme, or when a new emergence of flux from below destabilizes the configuration, the field lines break and reconnect in a lower energy state. That reconnection is a solar flare. The energy that was stored in the twisted field gets converted to kinetic energy of accelerated particles, thermal energy of superheated plasma, and electromagnetic radiation across the spectrum. A fraction of that energy goes into launching a CME, ejecting a huge bubble of plasma and magnetic field into space. The more energy that was stored, the more violent the release. Beta, gamma, delta regions store enormous amounts of energy because the shear zones are extensive and the field configurations are far from equilibrium, but not all beta, gamma, delta regions are equally dangerous. The devil, as always, is in the details. The size of the delta region matters. A small delta embedded in a large beta-gamma complex can produce significant flares, but a large delta with extensive shear zones has proportionally more stored energy. AR4294 does not have just one delta. It has multiple delta configurations scattered across its structure, creating a patchwork of magnetic shear zones that could rupture independently or in cascade. The depth of the flux emergence matters. Flux ropes that emerge from shallow depths in the convection zone tend to be less twisted than those rising from deeper down. The deeper the source, the more rotation the rope experiences during its rise, and the more twist gets wound into the field. Helioseismic observations of AR4294 suggest that at least some of its magnetic flux is originating from relatively deep in the convective zone, which implies high twist rates and correspondingly high stored energy. The rate of flux emergence matters. A region that develops slowly, with flux trickling up gradually over many days, has time to relax and settle into a more stable configuration. A region that emerges rapidly, with large amounts of flux punching through the surface over hours or days, remains highly dynamic and unstable. AR4294 showed rapid emergence, going from barely visible to massive in less than 48 hours. This rapid development suggests vigorous subsurface flows and a magnetic structure that has not had time to equilibrate. All of these factors point to AR4294 being not just beta-gamma-delta in classification, but beta-gamma-delta of the most dangerous variety. Large, deep-sourced, rapidly emerged, multiply-structured with several distinct delta configurations. And here is where our understanding becomes frustratingly limited. We can classify the magnetic structure, we can measure many of its properties, we can identify it as high risk, but we cannot predict when or even if it will unleash the major eruption it is capable of producing. Some beta-gamma-delta regions explode within hours of reaching full development. Others persist for days or even weeks, producing numerous moderate flares but never the big one. The AR3664 cluster that caused the May 2024 storm produced 12 X-class flares over 6 days. AR4294, despite being similarly complex, has so far produced only a handful of X-class events, and those were relatively modest, X1 to X2 level, rather than the X5 plus monsters that mark truly historic eruptions. Is this restraint temporary? Is AR4294 building toward a massive release, with each moderate flare relieving just enough stress to delay but not prevent the eventual catastrophic rupture? Or has the region already released most of its available energy in the flares and CMEs it has produced, leaving it energetically depleted and unlikely to generate anything more severe? These questions cannot be answered by looking at magnetograms alone. The two-dimensional maps of magnetic field at the visible surface tell us about the current state, but not about the dynamics, not about how much additional flux is still rising from below, not about the detailed three-dimensional structure of the field in the corona where the actual flares occur. To get at those questions, researchers use a technique called magnetic field extrapolation. They take the measured surface field and use mathematical models to calculate what the three-dimensional field structure above the surface must be, given the constraint that the field must be in a force-free or near force-free state. This gives a theoretical model of the coronal magnetic field, which can then be analysed for topological features associated with high flare probability. These features include magnetic null points where the field strength goes to zero and field lines from different sources meet, magnetic separatrix surfaces where small perturbations can cause field lines to jump discontinuously from one configuration to another, and quasi-separatrix layers where the field line connectivity changes rapidly over short distances. All of these are sites where magnetic reconnection can be triggered easily, where stored energy can be released explosively. Analysis of AR4294 using these techniques has identified multiple such features distributed throughout the modelled coronal field. The region is riddled with potential trigger sites for major eruptions, but identifying potential triggers does not tell you when or which one will actually fire. It is analogous to knowing that a building is structurally unsound, that the support beams are stressed beyond their design limits, that cracks are propagating through the concrete. You know the building could collapse, you know it is dangerous, but you cannot predict whether it will stand for another hour, another day, another week, or whether the next gust of wind will be the one that brings it down. AR4294 is that building. Its beta-gamma-delta classification is the engineering report saying the structure is compromised. The multiple delta configurations are the cracks in the foundation. The rapid emergence is the active degradation still in progress. And we are the occupants, knowing we are in danger but unable to determine how imminent that danger is. So we watch the region carefully. We monitor every small flare, looking for patterns that might indicate an impending major event. We track changes in the magnetic structure, searching for signs of increasing instability. We run models continuously, updating them with each new dataset, hoping to catch the warning signs before the catastrophic release. But the Sun is under no obligation to provide those warning signs. Flares can erupt without precursors, going from quiet to X-class in minutes. The magnetic field can appear stable right up until the moment it ruptures. The beta-gamma-delta classification tells us that AR4294 is capable of violence. It does not tell us whether that violence is inevitable, imminent, or already past. And this fundamental uncertainty is why space weather forecasting remains as much an art as a science. Why experienced forecasters develop intuition that goes beyond what the models and data strictly support. Why the decision of whether to issue a high-level alert for a region like AR4294 involves judgment calls that cannot be reduced to algorithm. The magnetic signature of chaos is clear. Beta-gamma-delta. Delta configurations pressed together, shear zones storing enormous energy. The architecture of instability laid bare in the magnetograms for anyone trained to read them. What comes next is written in magnetic field lines we cannot see. In plasma dynamics we can only partially measure. In a stellar interior we cannot directly observe. The equations exist. The physics is understood in principle. But the predictability, the certainty that would allow us to say with confidence that AR4294 will or will not produce a Carrington scale event in the next week, remains beyond our grasp. So the classification stands: beta gamma delta, extreme complexity, high risk. And we wait to see whether potential becomes actuality. 2024, the year the Sun remembered its power. 2024 will be remembered as the year the Sun reminded us that solar cycle. 25 is not a week cycle, it is not even an average cycle. It is shaping up to be one of the most active cycles in decades, possibly since the peak of the modern maximum in the 1980s and 90s. The statistics tell the story in stark terms. Between January 1st and December 10th, 2024, the Sun produced over 50 X-class solar flares. 50! That is the highest annual count since systematic X-ray monitoring of solar flares began in 1976. The previous record was set in 1991 during solar cycle 22, one of the strongest cycles of the modern maximum, when 48 X-class flares were recorded. 2024 exceeded that record by early December, and the year is not over yet. There are still weeks remaining for additional events. The final count could reach 60 or higher. But the significance goes beyond just the raw number of X-class flares. It is the distribution, the clustering, the production of multiple extreme events in rapid succession that marks 2024 as exceptional. In May, AR3664 produced 12 X-class flares in 6 days. That concentration of powerful eruptions from a single active region is nearly unprecedented. The flare sequence included multiple events above X5, with the strongest reaching X8.7. The resulting CMEs created the first G5 geomagnetic storm in over 20 years, with auroras visible in Mexico and India. Then came October. On October 1st, AR3842 unleashed an X7.1 flare. 2 days later, the same region fired an X9.0, the strongest individual flare of solar cycle 25 and the second strongest of the 21st century. These were not limb events, not glancing blows. They were well-aimed eruptions from regions near solar center with direct implications for Earth. The October 3rd of X9 flare did not produce a severe geomagnetic storm only because the associated CME's magnetic field happened to be oriented in a way that limited its coupling with Earth's magnetosphere. We got lucky. The energy was there. The CME was Earth-directed. But the magnetic field geometry was not optimal for driving reconnection. If that field had been rotated by 90 degrees, if the BZ component had been strongly southward instead of neutral, October could have seen a repeat or even an exceedance of the May superstorm. November brought its own dramatics. AR4294 produced an X5.16 flare on November 11th, the strongest event of that month and the sixth largest of the entire cycle. The CME from that flare was tracked as it raced toward Earth at nearly 2,000 kilometers per second, one of the fastest CMEs of the cycle. NOAA issued a rare G4 storm watch, anticipating severe geomagnetic conditions. The storm reached G4 levels as predicted, producing widespread aurora displays and causing measurable disruptions to GPS systems and HF radio communications. It was the third major geomagnetic storm of 2024, making this the most geomagnetically active year since 2003. By any reasonable metric, 2024 was exceptional, but here is the truly remarkable aspect. All of this activity occurred during what was supposed to be the declining phase after solar maximum. If the August 2024 sunspot peak marked the true maximum of solar cycle 25, then the subsequent activity in September, October and November represents some of the most intense solar behavior ever recorded during a cycle's post-peak period. Typically, as a cycle declines from maximum toward minimum, activity decreases gradually. You see fewer sunspot groups, smaller active regions, less frequent and less powerful flares. The sun settles into a quieter state. That is not what happened in late 2024. The sun remained intensely active well past the supposed peak. Large complex regions continued to emerge. X-class flares continued to erupt at a rate more consistent with the rising phase or maximum phase of a cycle, not the declining phase. This sustained high activity is one of the strongest pieces of evidence that we have not yet passed the true solar maximum, that the August peak was either premature or represents the first summit of a double peak structure with more activity to come. Consider the historical pattern. Solar cycle 19, which peaked in 1958 and remains the strongest cycle in the modern record, showed sustained elevated activity for nearly 3 years around its maximum. The cycle did not have a sharp peak. It had a broad plateau with multiple surges of activity spread across 1957, 1958 and 1959. During that extended maximum, the sun produced some of the most powerful events ever recorded, including flares that saturated the instruments of the time and geomagnetic storms that caused widespread technological disruption. Solar cycle 25 appears to be following a similar pattern. The August 2024 peak may be like the 1957 peak of cycle 19, marking the beginning of an extended plateau rather than a single maximum followed by immediate decline. If so, we could see continued high activity throughout 2025 and potentially into 2026. What is driving this? Why is cycle 25 behaving so differently from the weak cycle that was predicted, and so differently from the weak cycle 24 that preceded it? One hypothesis involves the sun's meridional circulation, which is a slow poleward flow of plasma at the surface and a return equatorward flow at depth. This circulation acts like a conveyor belt, transporting magnetic flux from the active latitude bands toward the poles where it is submerged and carried back down to feed the dynamo. The strength and speed of this circulation affects the solar cycle by controlling how much flux is transported and how quickly the dynamo can process it. During solar cycle 24, the meridional flow was observed to be fast, which some researchers believe contributed to the cycle's weakness. Flux was being transported away from the active regions faster than it could accumulate, preventing the buildup of large complex sunspot groups. But measurements during solar cycle 25 show that the flow has slowed significantly, allowing flux to accumulate more effectively and produce larger, more persistent active regions. This change in meridional flow could explain why cycle 25 exceeded predictions. The dynamo models that were used to forecast the cycle were calibrated on data from cycle 24 and earlier cycles. If the meridional circulation changed between cycles, those models would be systematically biased toward predicting weaker activity than actually occurs. Another factor is the polar field strength at the end of the previous cycle. The Sun's polar magnetic field reverses polarity during each solar maximum and then builds up again during the declining phase. The strength of this polar field at solar minimum is thought to be predictive of the strength of the next cycle, with stronger polar fields producing stronger cycles. Cycle 24 had exceptionally weak polar fields at its minimum, which contributed to predictions that cycle 25 would also be weak. But observations during the early years of cycle 25 showed that the polar fields were rebuilding faster than expected, suggesting that the cycle would be stronger than the weak polar fields at the previous minimum would indicate. These are plausible explanations grounded in observed changes in solar behavior, but they also highlight how much we still do not fully understand about the mechanisms that control solar cycle strength and evolution. We can measure the meridional flow and polar fields, we can correlate them with cycle activity, but the causal relationships are complex and the predictive relationships are uncertain. The result is that solar cycle 25 has consistently surprised us. Every time we think we understand its behavior and can predict what comes next, the Sun does something unexpected. The cycle that was supposed to be weak turned out to be strong. The maximum that was supposed to peak in July 2025 peaked earlier and higher than predicted, and the activity that was supposed to decline after the peak has instead remained elevated. AR4294, emerging in late November 2025, is the latest in a series of large complex regions that define 2024 and the ongoing behavior of solar cycle 25. It is not an anomaly. It is a pattern. The Sun is producing these monsters regularly, more regularly than the historical averages would suggest for a cycle at this stage, and this raises an uncomfortable question. If 2024 was extraordinary, if we set records for X-class flare production and saw 3 major geomagnetic storms in a single year, what does that tell us about the probability of an even more extreme event? The statistics of rare events are tricky. The fact that we have seen multiple X7, X8 and X9 flares in 2024 does not directly tell us the probability of seeing an X45 flare. Extreme events are not simply the tail of a smooth distribution that we can extrapolate from the more common events. They often involve different physics, different conditions, different mechanisms that only operate when certain thresholds are exceeded. But there is a general principle in complex systems. Increased activity at moderate levels often indicates increased probability at extreme levels. If the Sun is producing X-class flares at twice the historical rate, it is reasonable to infer that the probability of producing an extreme X-class flare, something in the X20 to X50 range, is also elevated compared to normal. How much elevated? We cannot quantify it precisely, but the qualitative assessment is clear. We are living through a period of heightened solar activity, and heightened activity means heightened risk of extreme events. 2024 proved that cycle 25 is capable of producing major events with significant Earth impacts. The May storm demonstrated vulnerabilities in our infrastructure. The October flares showed that the Sun can still surprise us with the sheer magnitude of individual eruptions. The November storm reminded us that even when we have advance warning and preparation, we still experience measurable impacts. Now we're in December 2025 with AR4294 facing Earth, and the question is not whether the Sun is capable of producing a major event. 2024 answered that decisively. The question is whether this particular region, at this particular time, will be the one that produces an event that exceeds everything we saw in 2024. Whether it will be the region that takes us from record-breaking activity to truly historic, civilization-scale challenge activity. The year 2024 was the year the Sun remembered its power. remembered that even at what was supposed to be a weak solar maximum, it could produce events that stress our technology and test our resilience. It was a warning year, a demonstration that the threat is real and present. Now the question is whether 2025 will be the year the Sun demonstrates the full extent of that power, the year we stop talking about Carrington-scale events as hypothetical possibilities and start dealing with them as actual realities. AR4294 is positioned to answer that question. The year 2024 set the stage. The final act, if it comes, will play out in the weeks ahead as this monster cluster makes its transit across the Earth-facing solar disk, and we watch, armed with all the data and models and preparation that 2024 taught us we need, hoping it is enough while knowing that the Sun cares nothing for our preparations or our hopes. The December convergence, multiple CMEs racing toward Earth. December 9th, 2025. Multiple coronal mass ejections are currently in transit between the Sun and Earth. Their arrival times overlap, their trajectories converge, and their combined effects could produce geomagnetic conditions that exceed anything we have seen since the May 2024 superstorm. This is not speculation. This is the current forecast from NOAA's Space Weather Prediction Center, issued with the kind of carefully worded urgency that indicates genuine concern from forecasters who have seen many storms but recognize that this situation has the potential to be exceptional. The sequence began on December 6th when AR4294, a region that emerged near the Sun's north-central position, produced an M8.1 flare. That alone would be noteworthy. M8.1 is just barely below the threshold for X-class classification. It represents a massive release of energy, and coronagraph imagery confirmed that it launched a full halo CME, the kind of eruption that sends plasma racing outward in all directions, with a significant portion of the ejector aimed directly at Earth. The M8.1 CME was modelled as arriving at Earth on December 9th, between 0400 and 0800 UTC. That gives the storm a predicted onset in the early morning hours, when most of the Western Hemisphere is in darkness but the Sun-facing side of Earth is experiencing daylight across Asia and the Pacific. The initial forecast called for G3 geomagnetic storm levels, strong but not extreme. Power grid operators were notified. Satellite controllers reviewed their contingency plans. Aurora photographers prepared to head north or to higher latitudes where the lights would be visible. But then the situation evolved. AR4294, which had been relatively quiet after its initial burst of activity when it first rotated into view, suddenly reactivated. On December the 7th and 8th, the region produced a series of M-class flares, including several above M3 that showed clear signatures of associated CME launches. These were not full halo events like the M8.1, but they were substantial eruptions with trajectories that modelling suggested would at least partially intersect Earth. By December 8th, NOAA's forecast had been upgraded. The M8.1 CME was now expected to be followed by additional plasma clouds from AR4294's renewed activity. The separate arrivals would happen within hours of each other, creating a compound storm event where the magnetosphere is hit repeatedly before it can recover from the initial impact. This is a dangerous scenario. The first CME arrival disturbs Earth's magnetosphere, compressing it, injecting energy and particles, creating geomagnetic storm conditions. Normally, after a few hours to a day, the magnetosphere begins to relax and recover. But if a second CME arrives during that recovery phase, it encounters a magnetosphere that is already stressed, already depleted of plasma, already reconfigured from its normal state. The second impact can be disproportionately effective at driving additional geomagnetic activity because the defences are already compromised. It is like getting hit twice in the same spot before the bruise from the first impact has had time to heal. The second blow does more damage than it would have if it had landed on healthy tissue. The May 2024 superstorm was a compound event. Multiple CMEs arrived in sequence over approximately 12 hours, each one built on the disturbance created by the previous arrivals, driving the geomagnetic indices higher and higher until the storm reached G5 extreme levels. The individual CMEs might have produced G2 or G3 storms if they had arrived separately. But arriving together, overlapping, reinforcing each other's effects, they created something far more severe. Now, December 2025 presents a similar setup. The 8.1 CME from AR4294 is substantial enough to drive significant geomagnetic activity on its own. The additional CMEs from AR4294, while individually less energetic, arrive at a time when the magnetosphere will be maximally vulnerable. The forecast models show the potential for G3 conditions escalating to G4, possibly even briefly touching G5 if the magnetic field orientations align unfavourably. And there is another factor that makes this situation particularly concerning. The December CMEs are arriving during a period when Earth is already experiencing elevated geomagnetic activity from previous events. Throughout late November and early December, the Sun produced a steady stream of smaller CMEs and high-speed solar wind streams from coronal holes. None of these individually caused major storms, but they kept the magnetosphere in a state of mild to moderate disturbance. The baseline geomagnetic conditions going into the December 9th event are elevated compared to a truly quiet period. This matters because magnetospheric response to solar wind forcing is non-linear. The same CME impact will produce different geomagnetic effects depending on the pre-existing state of the magnetosphere. A magnetosphere that is already somewhat disturbed will respond more strongly to additional forcing than one that is completely quiet. Think of it like priming a pump. The first bit of water you pour in might not produce any output because it is just filling the pipes and chambers. But once the system is primed, additional input produces immediate output. The magnetosphere works similarly. A CME hitting a quiet magnetosphere has to first overcome certain thresholds and initialize certain processes before major geomagnetic activity begins. But if those processes are already active, if the system is already primed from previous disturbances, then the same CME can drive stronger responses more quickly. So the December convergence is not just about multiple CMEs arriving at Earth within a compressed time window. It is about those CMEs arriving when the magnetosphere is already in a state that makes it more susceptible to strong geomagnetic responses. NOAA's forecast discussion makes this clear, noting that the elevated background conditions increase the probability that the storm will exceed the nominal G3 prediction. The language is careful, hedged with the uncertainties that are inherent in space weather forecasting, but the message is clear. This is a situation to watch closely, a setup that has the potential to produce significant impacts. What would a G4 storm mean for Earth in December 2025? Power grids at high latitudes would experience voltage control problems. Some protective systems might trip, causing localized outages that could last minutes to hours while operators work to restore service. Transformers in particularly vulnerable positions, especially older units that lack modern protective features, could suffer damage that takes them offline for extended periods requiring repair or replacement. Satellites would face increased radiation exposure and heightened risk of operational anomalies. Spacecraft in geostationary orbit, already vulnerable due to their position outside Earth's protective magnetosphere, would be at highest risk. Low Earth orbit satellites would experience increased atmospheric drag, requiring orbital adjustments that consume limited fuel reserves. Communication and navigation satellites might need to switch to backup systems or reduced capability modes to protect sensitive components. GPS accuracy would degrade significantly. The ionospheric disturbances caused by the geomagnetic storm would refract and scatter the satellite signals, introducing errors that make precision applications unreliable. Agriculture, which depends on centimetre-level accuracy for automated planting and harvesting equipment, could face disruptions. Aviation, especially on polar and high-latitude routes, would need to implement alternate navigation procedures. Surveying and construction projects that use GPS for positioning would need to halt work or accept reduced precision. High-frequency radio communications would be severely degraded or completely blacked out at high latitudes. This affects emergency services, military operations, airline communications on polar routes, and amateur radio operators. The blackout could last for the duration of the storm and potentially longer as the ionosphere recovers, and aurora. The visual effects of a G4 storm are spectacular. Aurora would be visible well into mid-latitudes, potentially as far south as California and Virginia, in North America, Southern Europe, Northern China and Southern Australia, in their respective hemispheres. For millions of people who have never seen auroral displays, it would be a once-in-a-lifetime experience. For the operators managing the technological systems being stressed by the same geomagnetic disturbance that creates those beautiful lights, it would be a tense and demanding period requiring constant vigilance and rapid decision-making. All of this from a G4 storm, which is not even the worst case. If conditions align such that the storm reaches G5, if the CME magnetic fields are oriented for maximum coupling, if the sequence of arrivals creates optimal conditions for driving extreme geomagnetic activity, then the impacts scale up proportionally. The May 2024 G5 storm caused $500 million in agricultural losses alone. It forced airlines to reroute dozens of flights. It created orbital tracking uncertainties that elevated collision risks for satellites. It stressed power grids across multiple continents. And it demonstrated that even with days of advance warning and extensive preparation, our technological infrastructure remains vulnerable. A December G5 storm would test those same systems again, this time during winter in the Northern Hemisphere when power demand is higher, when weather conditions might complicate recovery efforts if outages occur, when the social and economic impacts of disruption could be amplified by the season. But focus too much on the impacts and you miss the deeper message of the December convergence. This is not a unique event. This is becoming the new normal. Throughout solar cycle 25, we have seen repeated episodes of multiple CMEs launching in close succession, arriving at Earth in overlapping time windows, creating compound storm effects. It happened in May, it happened in November, now it is happening again in December, and there is no reason to think it will stop happening as long as the sun remains near solar maximum. We are living through a period when the sun regularly produces these cluster events, when the activity levels are high enough that multiple active regions can fire simultaneously or in rapid sequence, when the geometry favours Earth-directed trajectories more often than random chance would suggest. Some of this is just statistics. During solar maximum, there are more sunspots, more active regions, more flares, and therefore more opportunities for compound events. But 2024 has exceeded even solar maximum expectations, producing activity at rates that suggest something more than just normal maximum phase behaviour. Whatever the explanation, the operational reality for space weather forecasters and infrastructure operators is clear. We need to be prepared for compound events not as rare occurrences, but as regular features of the space weather environment during this solar cycle. The December convergence is not an anomaly. It is an example of what we should expect repeatedly over the next year or two, and that changes the risk calculus significantly. A single major storm that occurs once per decade is a manageable risk. You prepare for it, you weather it, you recover, and you have years to rebuild before the next one. But multiple major storms per year, year after year, each one testing the same systems, stressing the same infrastructure, consuming the same emergency response resources, that creates cumulative damage and cumulative risk that is much harder to manage. The December convergence is happening now. Multiple CMEs are racing toward Earth. Within hours, we will know whether the forecast of G3 escalating to possible G4 is accurate or conservative. We will see whether the magnetic field orientations favour intense coupling. We will discover whether our preparation measures, informed by the lessons of May and previous events, are adequate to protect our critical infrastructure. And then, assuming we survive this event without major failures, we will prepare for the next one. Because with AR4294 still facing Earth, still magnetically complex, still capable of major eruptions, the convergence we are experiencing now might not be the last one of December, it might just be the first. The preparation paradox. Living between cycles of fire, we have spent the last 2 hours exploring a sunspot cluster that is 90% the size of the one that nearly destroyed the technological infrastructure of 1859, a solar cycle that exceeded every prediction and produced record-breaking activity throughout 2024, and a sequence of geomagnetic storms that demonstrated both our vulnerabilities and our resilience. Now we arrive at the question that matters most. What do we actually do with this knowledge? The preparation paradox is simple to state but difficult to resolve. We know that a Carrington scale event will occur eventually. The Sun has produced such events in the past. It will produce them again in the future. The question is not if but when. And yet, We cannot sustain maximum alert status indefinitely. We cannot keep infrastructure in emergency protective modes year after year. We cannot operate our technological civilization as if the catastrophe is imminent every single day. But we also cannot relax completely, because the evidence suggests we are living through a period of elevated risk. Solar cycle. 25 has proven more active than predicted. AR4294 is facing Earth right now with the magnetic complexity and physical scale to produce a historic eruption. Multiple CMEs are in flight as we speak. The threat is not theoretical, it is current. So how do we live in this space between certainty that the threat exists and uncertainty about when it will manifest? How do we balance preparation against complacency, vigilance against exhaustion? The answer is that we do what humans have always done when facing large-scale but probabilistic threats. We build resilience incrementally, we improve our warning systems, we harden our most critical infrastructure, we develop contingency plans and train the people who will need to execute them, and we accept that we cannot eliminate the risk, only reduce it to levels that allow society to function while remaining capable of responding when the event finally occurs. This is not satisfying. It lacks the clean resolution that stories are supposed to provide. There is no moment when we can declare victory, when we can say the problem is solved and the threat is neutralized. The sun will continue to threaten us for as long as we operate vulnerable technologies, which is to say forever. But incremental progress is still progress. The measures that were put in place after the October 2003 Halloween storms reduced the impact of the May 2024 superstorm. The lessons learned from May will reduce the impact of the next major event. Each cycle of threat and response makes us slightly better prepared, slightly more resilient, slightly more capable of absorbing disruption without cascading failures. Consider what has changed in the 2 decades since the Halloween storms. Power grid operators now monitor geomagnetic conditions in real time and have protocols for reducing system stress. During storms, satellite manufacturers incorporate additional radiation shielding and design systems with graceful degradation in mind, so that partial failures do not lead to total loss. GPS receivers have improved algorithms that can maintain accuracy even during moderate ionospheric disturbances. Airlines have procedures for rerouting flights when high-latitude communications are compromised. None of these measures individually provide complete protection, but collectively, they create a system that is more robust than it was, more capable of continuing essential functions even when under stress. The May storm demonstrated this. We experienced significant impacts, but we did not experience the kind of catastrophic cascading failures that worst-case scenarios predicted, so preparation works. It is not perfect, but it works. And that is encouraging because it means the effort and resources being invested in space weather preparedness are having real effects. But, and this is the critical qualification, the preparation is not yet adequate for a true Carrington-scale event. May was severe, October had the potential to be severe, the December convergence happening right now could be severe, but none of these, not even May at G5 levels, approach the intensity that a Carrington event would deliver. The Carrington flare was estimated at X45. The May storm's largest flare was X8.7. That is a factor of 5 difference. And because flare effects scale non-linearly, being 5 times stronger means the impacts could be an order of magnitude more severe. The Carrington CME reached Earth in 17.6 hours at 2,300 km per second. The May CMEs travelled at 800 to 1,000 km per second. That velocity difference translates to dramatically higher kinetic energy, more severe magnetospheric compression, stronger geomagnetically induced currents. A Carrington event today would test our systems at levels they have never been tested before. Not in the satellite era, not in the GPS era, not in the modern interconnected power grid era. We have models and simulations that attempt to predict what would happen. But models are only as good as the data they are based on, and we have no modern data for events at that extreme level. So we prepare based on incomplete knowledge, using extrapolations from moderate events to estimate extreme event impacts, hoping that the extrapolations are valid but knowing they might not be. This is the preparation paradox in its most uncomfortable form. We know we need to prepare for the worst case, but we do not actually know what the worst case will do to our systems, because it has never happened to these systems before. AR4294 represents a unique opportunity in this context. If it produces a major eruption, if it launches a fast CME with ideal magnetic field orientation, if we get something approaching but not quite reaching Carrington scale that would provide invaluable data, it would test our systems at levels beyond what may delivered but hopefully below the catastrophic threshold. It would reveal vulnerabilities we have not yet discovered and validate mitigation measures that we have not yet tested under truly extreme conditions. This is obviously not something we want to happen. The disruption and damage would be significant even if we survive without catastrophic failures. But if it does happen, if AR4294 gives us that test, we need to be ready to learn from it, to analyze every aspect of the response, to identify what worked and what did not, and to implement improvements before the next event. Because there will be a next event. Maybe not tomorrow, maybe not next year. But within the lifetime of our current infrastructure, probably within the next few decades, the Sun will produce another extreme event. The historical record is clear on this. Major solar storms occur with irregular frequency but unavoidable inevitability. We have been lucky so far during the space age. The July 2012 event missed us. The more extreme events in the historical record, like the May 1821 storm and the February 1872 storm, occurred before we had satellites and GPS and continental power grids, but luck runs out. Statistical probability catches up with you eventually. The longer we go operating vulnerable infrastructure in the line of fire from a star that regularly produces damaging eruptions, the higher the probability that we will experience a direct hit from an extreme event. So preparation is not optional. It is mandatory if we want our technological civilization to survive intact through the next Carrington event whenever it comes. And the preparation needs to be ongoing, continuous, adapting as we learn more about solar behavior and as our technology evolves and creates new vulnerabilities. This brings us to the role of research and forecasting. Better prediction does not prevent storms, but it does give us more time to prepare, and in space weather, time is everything. The difference between 2 hours and 2 days of warning could be the difference between manageable disruption and systemic failure. Current research focuses on several key areas: improving our ability to measure and model the magnetic fields in active regions, particularly the coronal fields that we cannot observe directly; developing better techniques for predicting CME trajectories and speeds, including the possibility of mid-transit acceleration through interactions; understanding the processes that determine CME magnetic field orientation, which is the single most important factor for geomagnetic storm severity, but the hardest to predict in advance. Progress in these areas is steady but slow. The physics is complex, the observations are difficult, the computational demands are enormous. We are not going to achieve perfect prediction, but we might be able to improve from the current 12 to 24 hours of useful warning to perhaps 48 to 72 hours. That would be transformative for emergency preparedness. We also need to continue building redundancy into critical systems. Single points of failure are unacceptable when the hazard is global and the recovery time could be weeks or months. Power grids need alternative transmission paths. Satellite networks need backup spacecraft ready to deploy. Communication systems need multiple independent channels. GPS needs terrestrial augmentation systems that can continue providing positioning services even if the satellite constellation is degraded. These are expensive measures. They require sustained investment over years and decades, and they are hard to justify politically because they are protection against a threat that might not manifest for years, that might be handled by a future administration or a future generation. This is the classic problem of long-term risk management in democratic societies. The incentive structure favors addressing immediate problems over preparing for future possibilities, but the cost of preparation is orders of magnitude less than the cost of recovery from an unprepared catastrophe. The economic analysis is clear. Spending billions over decades to harden infrastructure and improve forecasting is vastly preferable to spending trillions to rebuild after a Carrington-scale event destroys portions of the power grid, takes out hundreds of satellites, and disrupts global commerce for months. So the argument for continued investment in space weather preparedness is not just about protecting lives and property, though that alone would be sufficient justification. It is about protecting the economic foundations of modern civilization, ensuring that the systems we depend on for food production, energy distribution, communication, transportation, and commerce can continue to function even when the sun reminds us of its power. AR4294, whether it produces a major event or quietly decays and rotates off the Earth-facing disk, is a reminder that this is not an abstract future problem. This is a current, ongoing threat that requires continuous attention. Solar Cycle 25 is proving to be more active than expected. The frequency of large, complex active regions has increased. The number of X-class flares has set records. The geomagnetic storms have tested our systems repeatedly. We're in the fire already. The question is how much hotter it will get before the cycle peaks and begins to decline, and whether we will be ready when the inevitable extreme event finally arrives. The preparation paradox remains. We cannot sustain maximum alert indefinitely, but we also cannot relax. So we find a middle path. We maintain vigilance. We continue incremental improvements. We study each event and learn from it. We accept the uncertainty while still taking the threat seriously, and we trust that the cumulative effect of all these efforts will be sufficient when the test finally comes. We may not be ready for a perfect storm, for a Carrington event with every factor aligned for maximum impact, but we are more ready than we were, and we will be more ready tomorrow than we are today. That ongoing process of improvement, that commitment to learning and adapting, is how we live with the reality of a star that can strike at us without warning and with devastating power. AR4294 is still out there, still active, still facing Earth. The December CMEs are arriving as predicted, testing our systems, providing another data point for our models and another challenge for our operators. And behind it all, the sun continues its mysterious internal dance, generating magnetic fields, erupting periodically, sending energy and particles streaming through the solar system. We are passengers on a planet that orbits this variable star. We have built a civilization that depends on technologies vulnerable to that star's temper, and we have no choice but to live with that vulnerability while working constantly to reduce it, knowing that the work is never finished, that each solar cycle brings new challenges, and that someday the truly big one will arrive. When it does, we hope to be ready, not perfectly prepared, because perfect preparation is impossible, but prepared enough to survive, to recover, to rebuild what is damaged, and to emerge from the crisis with our technological capabilities intact and our resolve to continue improving our defenses strengthened by the experience. That is the best we can do, and it will have to be enough. Thank you for staying with me through this journey into the heart of our star's current awakening. The sun is a reminder that we live in a universe that is beautiful, powerful, and occasionally dangerous. Our task is to appreciate the beauty while respecting the power and preparing for the danger. If you found this exploration valuable, please consider liking this video and subscribing to the channel. It helps us continue creating these deep dives into the science that shapes our world. And tell me in the comments, are you watching the aurora forecasts? Have you seen the northern lights during this active cycle? What questions do you have about space weather and solar activity? The information presented here is based on current scientific understanding and recent observations. It is not intended as official forecasting or emergency guidance. For operational space weather information and warnings, always consult NOAA's Space Weather Prediction Center or your regional space weather service provider. While we strive for accuracy, solar activity is inherently unpredictable, and forecasts are subject to significant uncertainty. Thank you again for joining me in this exploration. Stay curious, stay informed, and perhaps, on a clear night when the geomagnetic conditions are favorable, look up at the sky. The auroras dancing across the polar regions are not just beautiful light shows. They are visible evidence of the ongoing interaction between our planet and our star, a reminder of the forces that shape our existence and the fragility of the technological shell we have built around ourselves. Good night, and clear skies to you all.